So, hello everyone again. This is lecture 6 part 2 of current electricity. In this lecture we will start with the further discussions of those examples which I left in the previous discussion regarding Kirchhoff's rules. So, in the previous lecture we understood that using only the series and parallel concept in a complex resistor is very tedious. Hence, we applied two different rules which are called as Kirchhoff's rules, and using that in the previous lecture in the example I explained you that using only those two rules, junction rule I can explain you how the currents are passing through each of the different resistors. Today we will move on with the loop rule and then that will be the end of that example, and then we will move on further. So, let me start here. So, I am Sameer Levankar, let us begin our discussion. Okay. So, right now we are on the 13th point, that is the Kirchhoff's rules. After the Kirchhoff's rule, we will move on with the applications of current electricity, that is Wheatstone bridge, or basically the application of Kirchhoff's rules, that are Wheatstone bridge, meter bridge and potentiometer. Okay. So, in the previous lecture I explained you this complete concept, that is how the currents are divided in different resistors. Let us move on with the loop rule today. Okay. So, now let us take a closed loop, that is A B C C dash E A. So, let me check where is this loop here. So, A B, where is A B? So, A B C C dash E A. So, this is that loop we will talk about here. So, this is that small loop, as you can see this is that small loop. Okay. So, let us move on with this loop, quite evident as it is a closed loop. So, how can we apply this relation here? So, first of all what is happening here, let me try to go on. Let us say if I am here, then as the current is flowing here, it will be nothing but minus I into 1, again I by 2, it will be minus I by 2 into 1, again it will be minus I into 1. So, this thing is done, this thing is done, this thing is done, then I move here and then there is a plus 10 volts here. Therefore, what I found was that this value is equal to nothing but 10 is equal to 2 plus 1 by 2 gives you 5 by 2, hence it will be equal to 5 by 2 into I. So, using this I can find out that I is equal to nothing but 10 into 2 by 5. So, this can be one of the example of how this thing has been explained here. Okay. So, here what we found out, so if I so they have explained this using IR concept. So, first of all the same thing has been explained here, that is nothing but minus IR due to this, minus 1 by 2 IR due to this, and minus IR due to this, plus epsilon. Why plus epsilon? Because we are going from minus to positive direction. Hence, using this explanation we can get that epsilon is equal to nothing but 5 by 2 IR, and hence we found out the value, as we know now we know the value of resistance here. Let us suppose for now we know the value of resistance here, that is equal to 1, and we can find out the value, that is epsilon is a function of current only. Now, the second concept here is that the equivalent resistance R equivalent of the network is what? The total equivalent resistance R equivalent to nothing but epsilon upon 3I. Why 3I? Because there is if we take this into consideration, let us suppose we assume that the current flowing in these three directions were I. So, applying a junction rule here, then the total current which is flowing inside should be equal to total current flowing outside, hence the total current which is flowing inside should be equal to 3I. Therefore, the complete equivalent resistance can be calculated as epsilon by complete total current, hence it will be epsilon upon 3I. We know the value of epsilon, which is equal to 5 by 2 IR upon 3I. I getting cancelled, then that will be equal to nothing but 5 by 6 multiplied by R. As the value of resistance is given to you as 1 ohms, therefore, the value of R equivalent is nothing but 5 by 6 ohms. So, no use of series resistors, no use of parallel resistors, just simple application of Kirchhoff's rules, and hence that is the end of this question. Therefore, what we found is that equivalent resistance is equal to 5 by 6 ohms, hence the first part is completed. Now, moving to the next part here, hence for epsilon is equal to 10 volts, the total current is equal to 3I in the network, therefore, it will 3I which is equal to 4 amperes. So, 4 amperes calculated just by putting here also, as you can see I also got the value of I is equal to 4 amperes, and hence this is the current through each of the resistors. So, in the current here this will have the current as 4 amperes, this will also have 4 amperes, but this I by 2 will have 2 amperes. Simple mathematical formulation and simple use of Kirchhoff's rules, and that is the end of this example also. Okay, let us move on with the next example. So, it should be noted that because of the symmetry of the network, the great power of Kirchhoff's rules has not been very apparent in example 3.5. In a general network, there will be no such simplification due to symmetry, and only by application of Kirchhoff's rules to junction and closed loops as many necessary to solve the unknowns in the network. It will be yesterday in example 3.6. So, till example 3.5 what we did was, it just says that this is a little symmetrical example. Why? Because the divisions are happening very evidently. Now, we will take one more example, I guess, in which we will find out that if it is unsymmetric also, we can apply the Kirchhoff's rules very easily. So, let us directly move on to that example only. So, please look over here carefully, do not go by the complexity of the example, it is very easy question. Okay. So, the question asks to determine the current in each branch of the network shown in the figure. So, finally, what we need to do is we just need to find out the value of currents, that is all. Okay. So, each branch of the network is, let us look over the solution now. So, each branch of the network is assigned an unknown current to be determined by the application of Kirchhoff's rules. So, what we did was, let us suppose first of all that the current, let me start from this assumption here. So, the current which is going away from the battery be, let us say I1, it has went here. Let us suppose the current which is going through this line AB is, let us say I2. So, by applying the junction rule, let us suppose this current is nothing but this current plus this current should be equal to I1. Quite evident, I1 plus minus I2 plus I2 gives you I1, hence this thing is proved here. So, till now we explained this point and this point. Let us move on to this portion here now. Now, what is happening at this portion? Again we are assuming that through this 5 volt battery the current I3 is flowing. So, now at this junction I2 plus I3 should be equal to this portion here, hence I wrote this as I2 plus I3. So, this thing is explained, this thing is explained, this thing is explained. Now, let us move on to this junction here. So, at this junction, that is point C here, the total current which is going from above is I2 plus I3, the total current which is moving away from this portion is I1. That means the current which should flow in this portion should be nothing but this minus this. Why? Let us say the current in this portion is IC. So, here I2 plus I3 is equal to I1 plus IC, hence IC is equal to I2 plus I3 minus I1, and hence you can find this portion here. So, hence we just assumed. So, basically we need 3 equations for the complete question to take place. So, I explained every point till now. Let us move on with the further discussions of this example. Okay. So, to reduce the number of unknowns at the outset, the first rule of Kirchhoff is used at every junction to assign the unknown current in each branch. Next, we then have 3 unknowns, that is I1, I2, I3, which can be found by applying the second rule of Kirchhoff to 3 different closed loops. So, what are the 3 closed loops which they take into consideration? So, Kirchhoff's second rule for the closed loop ADCA. So, ADCA, that means this loop here for you, ADCA. Next loop is ABCA, that means this loop has been taken into consideration here, and the third loop was BCDEB. So, BCD, where is E here? BCDEB. So, this is the third loop is taken into consideration. So, using these 3 loops we will get 3 different equations, and using that 3 equations we can find out the value of I1, I2 and I3. I guess using these 2 equations only our work will be done, because the third thing has been explained using the different considerations of I1, I2, I3. But for simplicity, for more clarity in the concept, we will use 3 equations and then we will find out the values as required. Okay. So, let us move on with the closed loop concept here. So, the first is about ADCA. So, ADCA. So, that means this loop been talked about here. So, let us move on. So, first of all, let me start from this portion here. So, there is an addition because we are moving from minus to plus direction, therefore, it will be plus 10. So, plus 10, then let us move on down. So, it will be minus IR. So, I is nothing but I1 minus I2 into 4. Then let us move up. So, it is opposite in direction to that movement of our loop. Therefore, it will be plus I2 plus I3 minus I1 into 2, and then we are going in the same direction as the current as the loop, that will be minus I1 into 1 equal to 0. So, if you look clearly, this is the first line being made here, that is 10 minus 4 into I1 minus I2 plus I2 plus I3 minus I1 into 2 minus I1 equal to 0. So, this is the first equation which we had. Let us move on to the second loop, that is ABCA. So, where is ABCA? Let me look, ABCA. So, this is the loop being talked about here. Okay. So, first of all, again we are moving in this direction. So, it will be plus 10 again minus I2 into 4 minus I2 plus I3 into 2 minus I1 into 1 equal to 0. So, if you look clearly, again this thing has been explained here. So, it is plus 10 minus 4 I2 minus 2 into I2 plus I3 minus I1 equal to 0. Hence, this is the second equation. Let us move on to the third equation now. So, for the closed loop BCDEB, so where is BCDEB? This is the third loop being talked about here. So, let us move on, let us start from this point here. So, because there is an addition minus to plus, there will be plus 5, then it will be minus I2 plus I3 into 4, then it will be next is minus I2 plus I3 minus I1 into 2, which is equal to 0. So, if you look clearly, this is the expression we talked about here, it is 5 minus 2 into it is 2 here, 2 into I2 plus I3 minus 2 into I2 plus I3 minus I1 equal to 0, and hence this is the third equation. Now, using 3 equations, 3 unknowns, we can find out the results. So, equations are 3 simultaneous equations in 3 unknowns. These can be solved by using usual method, which gives you I1 is equal to 2.5 amperes, I2 is equal to 5 by 8 amperes, and I3 is equal to 17 by 8 amperes. Therefore, the currents in the various branches of the network are, so now if we have I1, I2, I3 values, I2 is directly put, I3 is directly put, I1 is directly put, and here it is I1 minus I2, here it is I2 minus I3, and here it is I2 plus I3 minus I1. Hence, the complete circuit is analyzed. Okay, so therefore, the currents has been explained here, that is in AB, CA, DEB, AD, CD and BC. Okay, let us move on with the further discussions now. So, it is easily verified that the Kirchhoff's second rule applied to the remaining closed loop does not provide any additional independent equation. What does this line mean? Let us suppose I take this into loop, that is B A D C B. Even if you try to make the equation here, then the complete loop on the left hand direction will always give you value of 0 only. So, there is no addition loop, there is no use of that loop, hence we do not take into consideration. Similarly, if by example if I take this loop also, you may find that the value in the LHS only will give you 0. Okay. So, it is easily verified that Kirchhoff's second rule applied to the remaining closed loop does not provide any additional independent equation, that is the above values of current satisfy the second rule for every closed loop of the network. For example, total voltage drop across the closed loop BADEB. So, as you can see BADEB, you are taking a complete loop here. What happens is plus 5 volts plus 5 by 8 into 4 volts minus 15 by 8 into 4 volts, which is equal to 0 as required by Kirchhoff's second rule. So, using the other loops, we can try to find out that if we are doing the complete analysis which we did was correct or not. So, if we are getting the value of 0, hence our complete analysis is correct. Okay. So, this is the end of the complete Kirchhoff rules only. Let us move on with the further applications, such as the first application is the Wheatstone bridge. So, let me try to explain you what is a Wheatstone bridge. So, this is a peculiar example of a Wheatstone bridge. So, let us first of all look over this example only here. So, let me try to explain what is happening here. So, here this is a battery, quite evident. These batteries are connected to these two portions, that is this A and this C here. Then as you can see that a galvanometer has been put here between the portions B and D. What is a galvanometer? Galvanometer just explains that if a current is passing through this or not. So, it is a arrow kind of thing, it deflects from its original position if there is a current passing through it. Okay. Then these 4 are resistors, and now the basic use of these resistors will be dealt when we will go on with the further discussions of Wheatstone bridge. Okay. So, this is the complete application of this. Let us move on with the Wheatstone bridge now. So, as an application of Kirchhoff's rules, consider the circuit shown in the figure, which is called the Wheatstone bridge. So, this is called as a Wheatstone bridge. The bridge has 4 resistors R1, R2, R3 and R4. So, this is R1, this is R2, this is R3 and this is R4. Okay. Across one pair of diagonally opposite points A and C in the figure, a source is connected. So, as you can see that a source is connected across the opposite points A and C. Okay. This is called the battery arm. So, this AC is called as the battery arm. Between the other two vertices, that is B and D, a galvanometer G. What is a galvanometer? Which is a device to detect currents, is connected. So, as you can see the galvanometer is connected here. This line shown as BD in the figure is called as the galvanometer arm. So, this is called as the battery arm and this is called as the galvanometer arm. Okay. For simplicity, we assume that the cell has no internal resistance. So, the complete assumption, we started with the assumption that small r is equal to 0. Okay. Next is in general there will be currents flowing across all the resistors as well as a current Ig through capital G. So, there will be current, so there will be a current in this way, in this, in this, in this, in this. The current denoted in this grammar is denoted by Ig. Okay. Of special interest is the case of a balanced bridge. So, now what is a balanced bridge? It is a special interest, it is a special case in the multiplication or in a function of these 4 resistors. What is that case? That case, first of all, that case is called as a balanced bridge. What happens in a balanced bridge? The resistors are such that Ig is equal to 0. There will be a combination of these resistors such that the current flowing in this BD arm is 0. So, we can easily get the balance equation such that there is no current through G. So, now how to get this balance equation is the complete application of Wheatstone bridge. Okay. Let us move on. So, in this case the Kirchhoff's junction rule applied to junctions D and B immediately gives us the relation I1 is equal to I3 and I2 is equal to I4, quite evident. So, let us suppose that the currents flowing outside this junction is I1 and I2, therefore, I2 I1. So, here as you can see that I1 is equal to I3. Why is I1 equal to I3? Because we are going with a balanced condition in which the current passing through this is 0. So, let us suppose if this is 0, then there will be nothing coming from this direction, therefore, I1 is equal to I3 and similarly I2 is equal to I4. Okay. Next we apply Kirchhoff's loop rule to closed loop ADBA. So, let us apply the loop ADBA. So, let us suppose this is the first loop here. Second loop is CBDC. So, this is the second loop here. Okay. The first loop gives, so let us go with the first loop here. So, first loop is minus I1 into R1 minus I1 into R1. Next is because of this it will be 0. So, plus 0 and then again next will be minus I2, sorry not minus because the current direction in this direction here, so it will be plus. So, it will be plus I2 into R2 is equal to 0. So, this is the first equation which is written here. And the second loop gives, the second loop, let us go on with the second loop now. So, for this loop how to explain? So, it is I2. So, we are first of all assuming I2 here. So, it is I4 into R4 minus I3 into R3. As I2 is equal to I2 is equal to I4 and I1 is equal to I3, we can just write I4 as I2. So, I2 into R4 minus I3 can be written as I1 into R3 is equal to 0. Therefore, this is the second relation here. Now, using these two equations, just using the concepts. So, I1, just let me explain what is happening now. So, it is I1 R1 is equal to I2 R2. Say another one is I1 R3 is equal to I2 R4. Now, dividing the equations, what we get is R1 by R3 is equal to R2 by R4, or in much easier sense R2 by R1 is equal to R4 by R3, and this is complete relation, that is a complete function of balanced equation. So, what is happening here, as you can see quite evidently. So, R2 by R1. So, R2 by R1. So, division ratio of this should be equal to ratio of this, that is R4 by R3. So, this is the final condition of balanced, this is the balanced condition, this is the condition for a balanced condition of Wheatstone bridge. Let me stop it here, we will go on with the further discussions of Wheatstone in the next lecture here. For this, the conclusion is just that finally using this complete concept of Kirchhoff's rules, we found that the ratio of R2 by R1 should be equal to R4 by R3 for balanced condition. So, let me stop it here. Thank you.